Welcome to lecture here. All right, welcome to lecture, and we're just going to lecture for just a little bit, just kind of keep us on track. Obviously, we then will have our exam coming up afterwards, so we're going to lecture, get through some of these, a little bit of these calculations here involving buffers, and that should set us up nicely for next week in terms of the labs and stuff like that. And like I said, we'll take a little break and then off we'll go to take the actual exam. A reminder again, we'll talk a little bit about this at the end, but again, you do have to have your camera on, focused on your work area, and you need obviously just some paper, something to write with, and a non-graphing calculator to do it. And obviously, you need to be in the Zoom meeting um, while you're taking the exam, and we'll talk about all that kind of stuff towards the end here lecture. All right, so where we left off last time was we got into buffers, and we talked about what buffers were, and we had this idea of, again, a buffer is really either a weak acid and its conjugate base, or you could have a weak base and its conjugate acid. And those are really the two components of a buffer. And the reason that we need it to be a weak acid or a weak base is because those guys will be able to set up an equilibrium. And the purpose and the way a buffer works is, as we talked about last time, there's really in the solution to begin with in a buffer, there's an acid part to that buffer and there's a base part. So I think we called it BP there. So there's an acid part and a base part to that buffer. And because something is a weak acid or a weak base, it will be able to set up that equilibrium and keep both of those things in the solution. So like our acetic acid, sodium acetate example, if we make that the acetic acid is able to set up this equilibrium, and because it is able to do that, we're able to have, again, both of these guys in the solution and be able to be in that solution, again, our acid part here and our base part. And that's really good because that allows it to react with, when you add more acid or base to the buffer, to basically kind of prevent the formation of free H plus or more free OH minus, both of which would obviously affect the pH greatly. So the way we talked about it there, again, last time was, if you have this buffer here and you add some base to it, it's going to react with the acid part. So the acid part of the buffer will go down, but as a consequence of the reaction that occurs, we actually will make the base part of the buffer. So that's also something that's very common that happens in a buffer. You sort of have both the acid part and the base part there. And as one goes down, as it reacts, the other one is being made. So you're kind of regenerating almost part of the buffer, even though you're reacting part of the buffer as well. And that's why it's able to sort of maintain that pH for a good period of time, as long as everything's okay in terms of molarity and those type of things. And the same thing occurs on the other side there. If we add some acid to our buffer, it will react with the base part of the buffer and it will use up some of that base part, but the consequence is it will make some of the acid part. And ultimately, how a buffer works, as we talked about, is it prevents the formation of free H plus when you add acid. And because the H plus concentration is pretty much remains constant, the pH of that solution will also remain relatively constant. As we talked about, if you were monitoring it, you would see a slight decrease, for example, if you add some acid, but you won't see a tremendous jump in pH, like, again, it going from a pH of 8 all the way down like a pH of 2 or anything like that. Maybe it started at 8 and it went down to maybe 7, 9 or something like that. So you won't see these tremendously giant jumps in pH in a buffer solution. And again, that's different than if you try to make a buffer out of a strong acid or a strong base. Again, the reason you can't do that is, I'm going to try to find where I'm writing. There it is. If you take something like hydrochloric acid, it's going to break apart into H plus and Cl minus. And this is 100% what you would have in that solution. And as you would see, you would have none of the acid part in that solution anymore. You would just really have the conjugate base part, and it would have no way to really act as a buffer. So the components of a buffer must be weak acid, conjugate base, or the salt of its conjugate base must be a weak base, and the salt of its conjugate acid. Now, you cannot have a buffer that is directly made up of a strong acid or strong base. But like I mentioned last time, and it may seem confusing, and I'll try to point it out as we kind of go through maybe some examples where you could kind of see it. But you can actually generate a buffer from a reaction of a strong base and a weak acid. So, for example, if you took acetic acid, right, and you said, I want to make a buffer just from acetic acid, if you react it with something like sodium hydroxide, when it reacts, you will get, write that, right? You'll get water plus some sodium acetate. All right. Try that again. All right. I have it in my head. It's just not translating there to the screen. Let's try that again. All right. So if we do a reaction like this, or a double displacement reaction there, and I keep on running the C first. Let's go this way. Okay. There we go. All right, I need a nap. I know it's 1:30 in the afternoon, but I might need a nap. All right, so it is acetic acid plus some sodium hydroxide, make some sodium acetate, and some water. Now, you could generate a buffer by doing this, and we'll actually see this in titrations when we talk about it. But if you do this reaction, the key is this is not a buffer, these two things. What will happen is you will have to use up all of the sodium hydroxide so that it is not left after the reaction is over. And what you would be left with would be just the acetic acid and the sodium acetate, which is a buffer. So it's sometimes referred to as you can make a buffer in situ, which means you could do it by doing a chemical reaction. But this thing does not turn into a buffer until all the sodium hydroxide is gone, and it's really these two guys, which again is our weak acid and conjugate base. So sometimes people get confused about that when they see, well, I can make a buffer with a strong acid or a strong base, but it's really not a buffer because the way that you do it is you almost make the strong acid, strong base like the limiting reagent, which means it gets used up 100%. So by the time the reaction is over, there's no more strong acid or strong base there, and you're left with just a buffer at the end of that. And we definitely will see that when we talk about a certain type of titrations, that is something that does occur. All right, let's let some people in. All right. Any questions on buffers and sort of how it works that we were talking about last time? Again, if you do have questions, feel free to ask them. Let's get back to where we were, I think. So we were here. We want to think about these guys. We want to determine which one of these sort of pairs would be a buffer or could be a buffer. So why don't you take a moment or two and sort of think about which one of these you think could be a buffer, which one maybe cannot be a buffer, and then we'll talk about it. Okay, so obviously, in order for something to be a buffer, they do have to be related to each other really through that acid conjugate base, right? Or base conjugate acid relationship, which at the basis of it is a difference of only one H plus. So when we look at A, that's KF and HF, A would be a buffer in that case, and that's because HF is a weak acid and KF is really his conjugate base, right? It's really the salt of his conjugate base. Again, as we talked about, what makes it the salt is the potassium's there. But ultimately, what this is HF and F minus, right? So A would be a buffer in this case. B is related to each other. We got HBr and we got KBr. Same deal. This is really HBr and Br minus. And this guy here is related to each other, but this is not a buffer, and that is because HBr is a strong acid, right? Remember, acid strength increases as you go down, group 7. And because it's a strong acid, I was just talking about, you cannot have a buffer that is made up of a strong acid. So that would not be a buffer system. And lastly here, C, we got really some carbonate, and we got some hydrogen carbonate, right? So they are definitely related to each other. Difference is just one H plus, and they would be a buffer from carbonic acid is basically where that's from. So that's a weak acid in its conjugate base, and that would be a buffer. So looks like A and C here are buffers. B, not so much there. Any questions on that? Okay. So let's talk about how we can sort of solve these buffer type programs, I guess. It'll be a short buffer program here in a second. Our problems, I guess is a better word there. And again, remember that we saw a really important equation that is used for common ions. And again, a reminder that really common ions is buffers. So buffers are a common ion effect. And again, that was the Henderson-Hasselbalch equation, which you could use. You could use that equation in a buffer situation, and that's the only time really you should use it is a buffer situation. You could also use an ice table if you chose to do so, like we talked about last time. You could do it again either way. So why don't you start with, let's see here. Why don't you start with part A and see what you get? And then we'll talk about part A, and then we'll do part B together, as there's some things we need to talk about in terms of how to do part B. So right now, do part A, and then we will see if we all get the same answer. Okay, so let's talk about part A. So part A, we are calculating the pH of a buffer that's made up of acetic acid and sodium acetate. So as we saw, that's a popular buffer sort of solution. That's a weak acid and it's conjugate base. Again, if you're not sure, acetic acid is a weak acid. We talked about last time, a lot of information and problems that help you make those decisions. So we see a Ka value, obviously, for acetic acid. So again, that's a very big hint that it is a weak acid. So as you know, it's a buffer situation. So you can go directly into the Henderson-Hasselbalch equation using the pH equals the pKa plus the log of the base over the acid. Remember that the pKa value is minus the log of the Ka. I'm going to write it right this time, I think. That is minus the log of 1.8 times 10 to the minus 5. And that should give us a pKa value of 4.74. In this case, we can then go right into our Henderson-Hasselbalch, which would give us 4.74 plus the log. And in this case, the concentration of our acid and our base are both 1 molar. So you can't really mess that up, I think. That is 1 divided by 1. Log of 1 is going to equal 0, right? And that means that the pH of this solution opening up in part A is 4.74. Now, again, a reminder that if you don't want to use the Henderson-Hasselbalch equation in this case, you could still do an ice table. So the ice table would really just be the weak acid breaking apart. And initially you would have 1 molar of this guy, 0 this guy. And again, the key here is here to make this really a buffer program or problem, you do have a concentration to begin with. And again, people always kind of screw it up. If they choose the ice table, they always leave that one as 0 as well. And obviously this goes into the Ka value. That will get you X when you solve for it. And obviously that is your H plus, and it should get you back here to our original answer that you got with the Henderson-Hasselbalch equation. So again, you do have some options as we talked about last time. I personally think Henderson-Hasselbalch is a good way to go, but you do not have to do that. So you're not required, obviously, to use it. You can use a nice table if you like to do it that way. Sort of better. It's perfectly fine. Any questions on part A of this problem? Kind of like what we were talking about last time. All right, so let's talk about part B here and see what it says. So now what we want to do is we want to take that buffer that was made and we want to add, we want to know what the pH is after we add 0.1 molar hydrochloric acid to the buffer. In this particular problem, and not in all problems, but in this particular problem, we're going to assume that all the volumes are pretty much going to be 1 liter. So that will make the math a little bit easy. Other times it's not going to be assumed that everything will stay the same volume. So you do have to take it into account. So let's kind of set this up here. So we have our buffer. So we basically have 1 liter of our 1.0 molar acetic acid and our 1 molar sodium acetate. And we're going to add to it, it was 0.1 molar, right? Yeah. 0.1 molar HCl. So a couple of things which is really important, especially in this chapter, is the idea of molarity. So let's just talk a little bit about molarity. Molarity is moles per liter. Now, when you add volume, do some type of dilution, mix some solutions together, hopefully you know that the molarity will change, right? Because as you add that volume, the liters of solution, which is the bottom part of molarity, gets bigger. The molarity continuously changes. The one thing that really doesn't change if you sort of mix a bunch of solutions together is actually the moles part. So the moles part remains relatively constant. The molarity changes. So a very big, important thing whenever we do any situation where we are adding volumes together, when we do our ice table, we actually have to do the ice table in moles. So you do have to do the ice table in moles. You cannot do it in molarity because the volume will continuously change and you will get sort of the wrong answer. So this occurs in this situation that we're talking about right now where we have a buffer and we want to add something to it. It occurs continuously in the next topic we're going to talk about, which is titration. So if you've done a titration before, I hope you have if you're sitting here, you know that you are doing nothing but constantly adding volume, right? So you're just constantly adding volume. The molarity is going to change over everywhere you add that volume. But again, the number of moles you start with in a solution is the total number of moles that are available really to react. And when we react two solutions together, it's really not the molarity per se that's reacting. It's actually the moles of the solute that's in there, right? You only have a certain amount of solute floating around that's available to react. So I'll get to your question in a little bit, okay, when I get a chance. So it is extremely important whenever you do anything that involves adding volume to a solution that you do the ice table and moles. Now, what's going to happen typically is you'll have to do at least one ice table usually. You might have to do two ice tables, but at least the first ice table that you do that involves reacting, you do need to do it in moles. After you're done with the first ice table, you then can convert back to molarity. So it's really good practice to first ice table when you're mixing solutions, do it in moles. At the end of that ice table, you want to convert it back to molarity, and that's usually very good practice. So let us take a look at what's happening here. So since we're assuming everybody's 1 liter, that's going to make the moles really good. So when we add hydrochloric acid to our buffer, it is going to react with not the acid part, right? It's going to react with the base part, right? So it's like a acid-base reaction. So the reaction we're actually going to get is HCl. That's going to react with the base part of the buffer, which is sodium acetate. And we're going to get like a little double displacement type deal going on here. Excuse me. And we will get, what do we get there? We'll get some acetic acid. That's good. And we will get some sodium chloride here. And initially here, we want to do our initial in moles. So we're going to assume 1 liter of 0.1 molar HCl. So if you take 1 times 0.1, we get 0.1 moles. Yeah. Our acetate, we have 1 liter of the buffer. So 1 liter times 1 is 1 mole. 1 mole over here. So remember, it is a buffer. So again, people always forget about the buffer part on the other side, especially when they do these ice tables. Now, we're going to have 0 here of sodium chloride. The deal with sodium chloride is, as we talked about last time, that is a neutral salt, which means, truthfully, I'm not even going to worry about sodium chloride. So I'm not tempted to do anything with it or anything like that. Also slightly different than our normal ice table we've done to this point. Normally at this point, we go minus x, plus x, and all that good stuff. And x is the change that occurs. But if this is truly a buffer and it is truly functioning correctly, we should know that all of the HCl that we just added should actually be used up. And we should know that it is actually the limiting reagent. And the change part here is actually going to be the moles of the HCl in this case, because it should get completely used up. By the way, logic tells us smaller number here, yes, is the limiting reagent. So you can't use up the other guy. Otherwise, you're going to have a negative number, which won't be good. And that means that at equilibrium, we got 0 of our HCl, which we would expect because it's a buffer. We would have, I'm going to use a calculator. It's a late day here today. 0.9 in terms of that, 0.9. And again, these are moles. And I'll do that by hand here, 1.1 moles, and hope for the best. Now, this is our ice table. Again, similar to what we did before, but because it's a buffer, because we know in this case the HCl should be used up, we actually can use the numbers there and get actual numbers at the end. You can see again that everything here is done in moles because we're adding again the HCl, so the molarity will change, but the moles will remain constant. And this is typically what your ice table should look like when you're adding some solution to a buffer. You should do it in moles. Now, it is very good practice at this point when you are done with it to, after you're done with the very first ice table, to convert those moles back to molarity. So we would convert it back to molarity by dividing by the total volume, which in this particular example, we're assuming is just 1 liter. In your case, in a real problem, maybe you started with 50 milliliters of the buffer, maybe you added 10 milliliters of acid, so 50 and 10 would give you 60 milliliters as your total volume. So again, if we're not keeping the volume constant, which is normally not the case, this would technically be your total volume at this point. The volume of the buffer you started with and the volume of whatever you added, the acid or the base to it. Obviously converted to liters. This is going to give us 0.9 molar and 1.1 molar on this side. Now, if you're like completely lost at this point and not really sure what's going on, your ice table can be very helpful for you to try to figure out, what you got going. Maybe you missed the part in the problem where it said, hey, this is a buffer. And you're like, I'm not sure if I still have a buffer. So if we actually look at our ice table, we see that at equilibrium, we have some sodium acetate there. And the only other thing that we have is acetic acid. We do in reality have sodium chloride, but not going to affect anything. And again, at this point, these two things are still a buffer, which means at this point, you do have two options. Because it's a buffer, you could go right into the Henderson-Hasselbalch equation, which would probably be the easiest move. Or alternative to that, if you wanted to do an ice table, you could do another ice table. And the ice table, again, I'll just kind of show you the start of it, would again be our weak acid, breaking apart into our acetate and H+. And our initial guys would come from our equilibrium concentrations from the first table. So this would be 1.1, this would be 0, this would be 0.9. And you could continue on with the ice table like normal, minus x's, plus x's, solve for x and get the H+ concentration. And you would get your pH from that using, again, the Ka value for acetic acid. But since this is a buffer, the easier move is probably just to go right into your Henderson-Hasselbalch equation. And since this is still really the same weak acid, it is still the same pKa value of 4.74. Yes, so at this point, this is molarity here. So I'll put the big M here. And you should use molarity here at this point. So again, typically the moles, the question was, can you use molarity, I think, in the second table? And the answer is yes. And the answer really is you should use molarity in the second table. So with moles, really, that first ice table is usually the only place where you're kind of use moles. And it's really, really good practice at the end of that first ice table, like I did here, is to convert those moles into molarity. And because usually after you do that first ice table, depending on the calculation that's coming next, you do usually need molarity. So you want to make sure that, you know, you have molarity. So in the case of the Henderson-Hasselbalch, you actually can leave it in moles, but for most other calculations, you do actually need it in molarity. So really good practice just to convert it back to molarity after that first ice table, and you usually will be okay in terms of any calculations come down the pike. We're going to go plus the log here of our base. So reminder, our base here is the sodium acetate, and that's going to be 0.9 on top and 1.1 on the bottom, which would be our acid. And if we do all that good stuff, 0.9 divided by 1.1, do a little log action on it, and add a 4.74 to it, we end up with a pH after we added the acid of 4.65. So let's talk about a couple of things here with that number. First off, the original pH of this buffer before we added the acid to it was 4.74. We added some acid to this buffer. The pH went down a little bit, right, to 4.65, so about the same in that area. But more importantly, it also went down in the right direction. And what I mean by that is we added acid, so we would expect the pH to go down a little bit. Remember, as I talked about, you will actually see the pH go down a little bit, but what we're talking about with buffers is you're not going to see a tremendous jump in pH downward. Now, if you did this calculation and you got a pH of like, I don't know, 4.85 or 4.9, sure, it didn't jump a lot, but that is definitely moving in the wrong direction, considering that you added acid in this case. So that's, again, another way you could kind of check everything's okay. You know, your buffer really did work pretty well. It only went down a little bit. And more importantly, it went down in the right direction because we added acid and the pH went down in the correct direction. Any questions on that? So let me, before we go to the next example, just sort of explain to you what I was talking about with the idea of buffer capacity, right? So where can I do that, I think? Let me try to find a spot. Maybe somewhere I didn't scribble on too much. Let's see. How about the opening page? That looks like a good page. So let's say we took this exact same buffer that we were just talking about in that particular example, and we had our 1 molar acetic acid and our 1 molar, obviously, sodium acetate. And again, we'll say we have 1 liter of it. And let's say that you decided you're going to add 1 liter of the HCl just like you did. And perhaps, you know, you're busy people. Perhaps you didn't really read the instructions all that well. And you went to the qual wall. We'll just use that as an example. You went to the qual wall there, and you didn't grab the bottle of 0.1 molar HCl. You decided, well, 18 molar sounds pretty close. So you went with the 18 molar HCl, and you decided to add it to this buffer, right? So again, we're going to do this in moles. So when we add the HCl, just like we did previously, the HCl would react with our sodium acetate. And again, we would get our acetic acid and our sodium chloride. Whoops, running out of room there at the end. Hang on a sec. There we go. Clean up my bad sodium chloride there. All right. Okay, so get some sodium chloride in there. There we go. All right, ACl. Now, when we do our ice table, initially we would now have 1 liter times 18. That's like 18 moles of HCl. We would then have our 1 mole of acetate and our 1 mole of our acetic acid. So in this particular case, when we go to see the change, hopefully you could recognize that, wow, we got a lot of this guy. That's like an excess reagent at this point. And that's going to turn your poor little sodium acetate into like the limiting reagent. So the change that's going to happen here is actually all of that sodium acetate that you have is going to get used up. And that means that when you reach equilibrium, you'll have like 17 moles of your HCl. You would have blown right through your sodium acetate, and you will have like 2 moles of your acetic acid there, which means, again, if you convert these guys into molarity, you can see from your ice table, at this point, you would have HCl in a very high quantity. You would also have acetic acid there. The acetic acid is going to obviously produce some H+. The HCl, which is a super strong acid, right, is going to produce a lot of H+. And this is what we were talking about earlier when we talked about buffer capacity. In this particular case, this buffer was not made to handle that many moles of HCl coming in. And essentially what we just did was blow right through the base part of the buffer, which clearly, as you can see in this example, will now allow us to generate a lot of H+. And because now we're generating a lot of H+, we would expect to see in this case the pH jump or drop tremendously because it's no longer a buffer. So that's why it's really important when you actually go to make a buffer that you make it in the correct molarity with the correct number of moles to really handle whatever acid or base moles you're going to do that. Because as I was mentioning before, although we think about molarity a lot as, oh, molarity is, you know, the thing that's there to react. In the terms of molarity, it really is the mole part of it that's reacting. And in this particular buffer, you only have 1 mole of each of those components available to react. So if you add in there, like we did in this example, way too many moles of HCl, there's no way that that buffer could really handle that. And it would no longer be able to basically act as a buffer and be an effective buffer because you basically, as I just mentioned, blew right through the base part of it. And at that point, you're just really, it's almost just like at that point, you're just dumping H+ in there, right? Because you're just dumping acids. It's kind of like when you do a titration and, you know, that little indicator turns pink and you decide, yeah, who needs to stop there? I'll just keep dumping, right? And you keep dumping your sodium hydroxide in there. You're just dumping more base in there and stuff like that. And you're just adding more OH-. And that's essentially what's happening in this case. So when we talk about buffer capacity, it's really important, like I mentioned, the concentration of the buffer itself and also the concentration of the acid or base you're going to add to the buffer in order for it to properly or effectively work to maintain the pH. Any questions on that? All right, so let's give you an example to do to make sure. So why don't you work on that next example, wherever that example was. Get over there. And whoops, too far. All right, so why don't you work on this example, and let me give you a Ka value here. Let me try to remember what the Ka value is. Let's go with the Ka value that you will need. The Ka for NH4 plus is 5.6 times 10 to the minus 10. So we're looking for 2 pHs here, the pH of the solution to begin with, and then the pH after we add 20 milliliters of sodium hydroxide to this buffer. So this problem, we are not keeping all the volumes constant, so you do need to take them into account. So what is the pH of the original buffer solution, and then what is the pH after you add 20 milliliters of 0.05 molar sodium hydroxide to 80 milliliters of the buffer. So take a few minutes or so and do that, and then we'll talk it over. Okay, so let's just take a look and see how we're doing. First off, we want to figure out what the pH of the buffer is to begin with. So because we already know it's a buffer, we could go right into the Henderson-Hasselbalch equation, or again, you could use an ice table if you wanted to. We would want to find the pKa value, which is minus the log of 5.6 times 10 to the minus 10. That should give us a 9.25 as our pKa value. And because we haven't done anything to the buffer, we don't have to worry about moles or anything like that. We could just use molarity, go right into it. So 9.25 plus the log. Now we do want to get our base. So again, if you're not sure what's going on here, you could kind of compare the two things that look alike, which are these two guys basically. And if you look at those two guys, you can see the guy on the right has an extra hydrogen. And since if anything, it has a hydrogen, so it should be an acid, right? That's the definition of an acid. And what we would want to do is have our NH4 plus as the acid. Otherwise, we can look at the Ka value here, which tells us it is an acid as well. So that would be what would go on the bottom. So we take 0.3 divided by 0.36 there on the bottom. So if we do that, we get 0.3 divided by 0.36. We're going to take the log of it plus 9.25. That gives us an opening pH here of 9.17 for our buffer. Any questions on that? Hopefully it unfroze, I hope. Yes. Any questions on the first part? Okay, so in the second part of this problem, that's good. I was a little worried I was going to be here all weekend frozen. That's good. So let's see. Let's change the color. Mix it up there. All right. In the second part, we're actually again now taking the same buffer, and we are adding some sodium hydroxide to it. So as we talked about before, we're adding volume. So we do want to do an ice table here. We do need to do an ice table to really see what's going to happen to our buffer concentrations. And we do need to do it in moles. So we need to figure out the moles of everybody. So we are adding 20 milliliters. So that's 0.02 liters times the molarity of our sodium hydroxide, which is 0.05 moles per liter. And that would get us 0.0020 there, 0.001 moles of sodium hydroxide. We would do the same thing for our buffer. So remember our buffer here, we have 80 milliliters of it. So we would take 0.08 times 0.3 molar for our ammonia, and that would give us 0.024 moles of ammonia. And again, I'm taking 0.08 times 0.3 to get that. We would also take 0.08 times 0.36 for our other component of the buffer, which would get us 0.0288 moles of our NH4Cl. Remember that the buffer, right, in this particular case, has both of those things in there to begin with. And the total volume is 80 milliliters. So the 80 milliliters in terms of volume works for both parts of the buffer because obviously they need to be in the same container to begin with. So at this point, we're ready to do a reaction. We're adding sodium hydroxide, which is a base, which means it is going to react with the acid part of the buffer. So our reaction will look something like NaOH plus a little ammonium chloride. Gonna give us some sodium chloride. We're gonna also get some water there. And maybe we'll get some NH3 going on as well. So we got a lot of stuff happening there. So initially, we have our sodium hydroxide, which is 0.001 moles. Again, we want to do it in moles. We have our ammonium chloride, which is 0.0288 moles. Sodium chloride, like normal, not going to worry about. Water, like normal, not going to worry about. But we, again, do have some ammonia over here, which makes it a buffer. Also going to use the moles of that guy. Any questions on that part of the table? Change part here, as we can see, the sodium hydroxide is a smaller number, so that's going to be like the limiting reagent. So we're going to go minus 0.001, minus 0.001, and plus 0.001. That's going to get us at equilibrium 0 of our sodium hydroxide, which we would expect it all to be used up. We're going to take 0.0288 minus 0.001, gives us 0.0278 moles. We're going to add on the other side 0.024 plus 0.001, 0.025 moles on this side. And that's what the first ice table should look like. Now, we can again use our ice table to figure out what's going on. I have ammonium chloride. I have ammonia here. This is still a buffer at this point, which means I could use the Henderson-Hasselbalch equation. As I mentioned last time, it is good practice after you do this first ice table to convert those back into molarity. So to convert them back into molarity, we need the total volume. We took 80 milliliters of the buffer. We added 20 milliliters of the base. That gives us a total volume at this point in the beaker of 100 milliliters, which means we want to take each of these moles and divide it by 0.1 liters. And if we do that on the guy on the left there, we get 0.278 molar. And if we do it on the right there, we should get 0.25 molar. I'll just write it here. And now, because it is still a buffer, you again could have two ways to do it. You can either ice table it, or again, the easier move would be probably go into your Henderson-Hasselbalch. So that's going to pH equals 9.25, still the same K value as above, still really the same buffer. The log of our base, so again, our base is the NH3, which would be 0.25, divided by our acid, which is 0.278, and that would get us 9.20 as the pH at this point. So we got this 9.20. Let's sort of make sure that it sort of makes sense. First off, we started at 9.17. We added some base. It went to 9.20. So that's not a tremendous jump in pH. So that's good. And more importantly, because we added sodium hydroxide, we would expect the pH to go up, and it did. So at least when it moved in the correct direction. Any questions on any part of that? Okay, we're gonna lay it up there for today in terms of lecture. That got us through buffers, which is really good. Again, a reminder on Monday, we're gonna do, again, the experiment from yesterday and Monday to kind of together. Again, they're both buffers, so we'll talk about what we'll do out of that on Monday. We have our exam coming up at 3, so you can have a half hour, kind of get yourself ready and everything like that. Figure out, again, hopefully, how you're going to print it, where you're going to print it, be ready to print it, and all that good stuff. Make sure you got your calculator. Make sure you got nothing else out other than something to write with, your test, and obviously a calculator. And in your work area, make sure you got your camera set up so I can obviously see your work area, your hands and your test and what you're kind of doing. And at 3 o'clock, you should log into the meeting. And at that point, once we're all kind of logged in, I will open up the exam, give you some instructions, and you could go print your exam and then obviously be in the video for the entire part. Just to give you a preview of some of the stuff, there will be an exam module. You'll have to go on there. There's some instructions on there. There's going to be an academic honesty agreement that you can electronically sign. And there'll also be one as part of your exam that you can sign if you like. But you do need to sign one of those at least. Once you do that, you'll be able to get to the exam and print it. At that point, if you need to go not be on camera to print it, you could go do that. But obviously, you should come back in an appropriate amount of time, not like 45 minutes later. Like my printer is super slow. It's one of those dot matrix ones. It did one letter at a time. So you need to print it and make sure that you come back. And all the exams do need to be done by hand, on paper, pencil, pen, crayon, whatever you want to use. But it does need to be done on some type of paper and by hand. So no kind of computer, tablet, any of that type of writing does need to be done by hand on any type of paper, or the test if you print it on that paper as well. You will access the exam through Canvas, and you do have to have your like I said, your camera enabled so I can see what's going on, and you do have to be obviously logged into the Zoom meeting for the entire exam until you are completed. Now, you can if you cannot print it. So you should hopefully be able to print it. If you can't do that, then you could do it on a regular piece of paper. And obviously you should be doing the right thing. Yes. But you should be able to have the Zoom open and all that kind of stuff. Now, we'll talk about it though, but when we get started, but as soon as you complete your exam, you will need to send me a private chat through Zoom that says you're completed your exam. You're going to go and upload it at that point. Okay. So I'll remind you that when we start. All right. So at this point, we will stop the lecturing at 3 o'clock. Everybody log in. We'll get everybody there. At that point, I will open up the module for the exam. You could take the first few minutes or so, whatever you need to print it out and come back, or if you can print it where you're at, that's good. But again, it does need to be on the entire time you're on there. As we also talked about last time, you should not walk away from the camera for any reason. Otherwise, that will result in a 0. If you walk away from the camera, you best be submitting your exam at that point if you want any credit for it. So if you need to use the restroom, any other facilities, whatever you need to do, take care of that in the next half hour and make sure you're good to go. You'll have the entire lab period to take the exam. So it'll be over about whatever, 6-ish, yeah, on top of that. Any other questions? Obviously, you should not have any other stuff out, notes, materials, other than what's going to be provided to you on the exam. There's a lot of questions coming really quick. Give me a second here. If for some reason it cuts out, you should find yourself logged back on as soon as possible. Yes. So try to keep it from crashing. Make sure you just, if it happens to crash, log back in like normal as soon as possible. Okay. All right. So hopefully that'll take care of everything. I think there was a question. Yeah. Well, let's hope it's not too much of an issue. All right. So if it does, just log back in. Again, it shouldn't take you 2 hours to log back in or 20 minutes to log back in. So just log back in. Okay. All right. Hopefully we won't have too much crashing. Hopefully. All right. There was a question how I got 0.024 moles. Just to answer it, you took 80 milliliters, converted to liters, 0.08 times 0.3, which is the molarity. All right, I'll see everybody about 3, okay? So for the person that had the question, I think I saw it go by. You took 0.08 liters, which was the volume, times 0.3, moles per liter, which was the molarity. All right, I'll see everybody about 3 o'clock.